In this video, we are going to learn about the real numbers. We will be following the book called Understanding Analysis by Stephen Abbott. The topics we will learn are sets, functions, and the triangle inequality, followed by the axiom of completeness, consequences of completeness, and finally cardinality. Let us start with sets. But what is a set? A set is any collection of objects, and the objects are the elements of the set. Given a set A, we use the notation x in A if x is an element of A. Otherwise, we denote it with x is not in A. There are two main set operations. The first is called the set union. It is denoted by the cup sign. The union is defined by that if x is in A union B, then x is in A or x is in B. The second operation is called the set intersection. It is defined by the cap sign. The intersection is defined by that if x is in A intersect B, then x is in A and x is in B. There is a special set called the empty set. It is the only set that contains no elements. The next topic is functions. A simple definition of functions is that it is a rule which connects two sets. But we need a rigorous definition. Given two sets A and B, a function from A to B is a rule or mapping that takes each element in A and associates it with a single element of B. We write it as f from A to B. The set A is called the domain of f, and the set B is called the codomain of f. Let us take a look at Dirichlet's function. It is defined by g of x equals to 1 if x is rational, and otherwise it is 0. The domain of G is the set of all real numbers, and the range is the set 0, 1. There is no algebraic formula for this function, and it is also extremely difficult to graph this function. The next topic is the triangle inequality. We are familiar with the absolute value function, and it is defined by x if x greater or equals to 0 and minus x if x is less than 0. There are two important properties from this. We get that the absolute value of the product of A and B is equal to the product of the individual absolute values. We also get that the absolute value of the sum of A and B is always less equals to the sum of their individual absolute values. This is called the triangle inequality. Let us now look at a theorem. It states that two real numbers A and B are equal if and only if, for every epsilon greater than 0, it follows that the absolute value of the differences is less than epsilon. This is an f and f only statement, so we must prove it both ways. Forward direction is that if A equals B, then for every epsilon greater than 0, it follows that the absolute of A minus B is less than epsilon. The converse is that for every epsilon greater than 0, it follows that the absolute of A minus B is less than epsilon, then we must have A equals to B. For the forward direction, we have that if A equals to B, then it is true that the difference is equal to 0. Then it is certain that 0 is less than epsilon no matter what epsilon is chosen. Then for the converse, let us prove it with contradiction. For the sake of contradiction, assume that A not equals B. Then we know that the absolute of A minus B is greater than 0, which we can set as our epsilon. We know that the absolute of A minus B is less than epsilon for all epsilon greater than 0. Then we get the following two statements. Absolute of A minus B is less than epsilon, and it also equals to epsilon. This is a contradiction, so our assumption is false. It must be that A equals to B, and this completes our proof. The next topic is the axiom of completeness. We have to ask ourselves what is a real number. A simple definition that it is an element from the union of rationals and irrationals. But we need a rigorous definition for the real number set. There is a property which holds true only for the set of real numbers called the axiom of completeness. It states that every non-empty subset of real numbers that is bounded above has a least upper bound. The axiom of completeness talks about bounded sets. A set A, which is a subset of the real numbers, is bounded above if there exists a real number B such that A is less than B for all numbers A in the set A. The number B is also called the upper bound for A. It also talks about least upper bounds. A real number S is the least upper bound for a subset A of real numbers if S is an upper bound for A, and if B is any upper bound for A, then S is less equals to B. A set can have multiple upper bounds, but only one least upper bound. Let us prove it. Let S1 and S2 be the two least upper bounds for a set. From the definition, we can assert that S1 less equals S2 and S2 less equals S1. This can only be true when S1 equals to S2. Thus, least upper bounds are unique. Let us take a look at an example. Consider the set which contains all the rationals whose square is less than 2. The set is bounded above, for example, by 2. In the set of reals, the least upper bound is the square root of 2, but this does not exist in the set of rationals. So it isn't possible to find the least upper bound here. There are a few consequences of the axiom of completeness. Let us take a look at one. The nested interval property states that for each natural number n, assume we are given a closed interval In. Assume also that each In contains In plus 1. Then the resulting sequence of closed intervals has a non-empty intersection. Let us prove it by considering the set of all left-hand points of the intervals. Since the intervals are nested, every right-hand point of the intervals serve as an upper bound for the set A. Therefore, a least upper bound exists. Let it be x. Consider a particular interval In. Because x is an upper bound for A, then An is less equals to x. We know that each Bn is an upper bound for A and x is the least upper bound. This implies x is less equals to Bn. If we combine both, we get that x is inside the interval An, Bn for all intervals. Hence the intersection is not empty and our proof is complete. The next consequence is called the Archimedean property. It says that given any real number x, there exists a natural number n, satisfying n is greater than x. Another way of stating this is that the natural number set is not bounded above. To prove this, assume that n is bounded above. By the axiom of completeness, n should have a least upper bound. Let it be alpha. If we consider alpha minus 1, then we no longer have an upper bound. So there is a natural number n satisfying alpha minus 1 less than n. This is also equivalent to alpha less than n plus 1. But n plus 1 is a natural number. This is a contradiction since alpha is supposed to be the least upper bound. Therefore, n is not bounded above and our proof is complete. The next two theorems are as follows. For every real number a and b with a less than b, there exists a rational number in between a and b, and there exists a real number whose square is equal to 2. This is left as an exercise for the viewer. The next topic is cardinality. It refers to the size of a set. There are three important definitions we need to know. A function f from a to b is 1 to 1 if a1 not equals a2 in a implies f of a1 not equals f of a2 in b. The function f is onto if, given any element in b, it is possible to find an element in a for which f of a equals to b. The set A has the same cardinality as b if there exists a function from f from a to b that is 1 to 1 and onto. A set is countable if a and the natural number set have the same cardinality. The set of rationals is countable. Let us prove this. Let us set the set A1 to contain only 0. For A2 and onwards, define An by the following set. We see that each An is finite and every rational appears in exactly one of these sets. The one-to-one with n is achieved by listing each element in An and our proof is complete. Here are two hard exercises for the viewer. Problem 1 is to prove the set of real numbers is uncountable. And problem 2 is to prove that the open interval 0, 1 is uncountable. Our video ends with this. If you like this video, consider liking and subscribing. Thank you for watching.